Hi everyone, in this video I'll explain molarity, a common unit for concentration in the world of chemistry. So remember that concentration is really just a way to keep track of how much solute is dissolved in a certain amount of solution. There's two important pieces of information you've got to keep track of. The first of those is the obvious one, and that is how much solute has been dissolved in the solution. Obviously more solute is going to lead to more concentration. The other important piece of information is the amount of solution that solute is dissolved in. I like to imagine 2 separate teaspoons of sugar. We add 1 teaspoon of sugar to a glass of water and with the other teaspoon of sugar to an entire swimming pool. Our life experience tells us that even though these 2 solutions contain the exact same amount of solute, there's still going to be very different solutions. The glass of water is going to be much sweeter because it's much more concentrated, whereas the swimming pool probably wouldn't taste sweet at all because it's much less concentrated. This highlights the importance not only of the amount of dissolved solute, but the amount of solution it's dissolved in. So in chemistry, there's lots of different ways that we can measure concentration, but all of them that you'll learn about will factor in these same 2 components in at least some way. The rest of this video is going to focus on just one way of measuring concentration called molarity. We're going to talk about molarity because it's probably the most common concentration unit in chemistry. So the symbol for molarity is a capital M, and the way you calculate a molarity is by dividing the moles of solute that have been dissolved in the solution by the volume of the solution in liters. You might notice right away that it factors in our 2 important pieces of information, the amount of dissolved solute, it does that in moles, and the amount of solution in liters. This formula is the key idea for the video, so make sure you pause, take a moment, and write it down. We'll end the video looking at some examples of how to use this molarity equation, but just realize moving forward I'm going to use a slightly shortened version that looks like this, moles over liters, instead of writing out all of these words. But keep in mind that moles refers to the moles of solute and liters refers to liters of solution. Let's take a look at our first example describing 1.3 moles of sodium chloride, that's table salt, being dissolved in water to create a 350 milliliter solution, and it's asking us to solve for the molarity of the NaCl. So it's always good practice here to start off by writing whatever equation you're going to use. Here we're solving for a molarity, so obviously I'm going to use the molarity equation. Now I can read my question again and start plugging things in where they belong. The very first thing it tells me in the equation is that there's 1.3 moles of sodium chloride. And since that is the solute, I can plug in 1.3 moles on top of my molarity fraction. The one issue I do have is the volume it gives me is in milliliters, and for molarity, that volume has to always be in liters. The conversion between milliliters and liters is found at the top of the video screen, but a quick shortcut is to take that decimal place and move it 3 to the left, 3 places to the left. That's technically dividing by 1,000 to change milliliters to liters. So the volume of my solution is 0.35 liters. All you've got to do now is divide those 2 numbers. After dividing, you get a value of 3.71, which is the molarity of the solution. The units the molarity should get is a capital M. Here's a different example describing a 0.5 liter solution created by dissolving 4.52 grams of iron 3 chloride. It's asking us to do the same thing as the last problem, solve for molarity, so I'm going to start off by writing my molarity formula, moles divided by liters. Now the easy part in this question is the volume, because it already gives me the units of volume in liters, so all I have to do is plug in 0.5. The hard part here is that it doesn't tell me how many moles of solute I have. Instead, it gives it to me in grams, and I can't plug in grams, so my first step is to convert those grams of iron 3 chloride into moles. To do that, I'll need to look up the molar mass of iron 3 chloride on a periodic table. So here's iron with a molar mass of 55.845, and here's chlorine with 35.45. But since the formula is FeCl3, I have to multiply chlorine's molar mass times 3 and then add it to the iron's molar mass of 55.8. So here you can see the work to find that molar mass with the iron's molar mass added to the 3 chlorine molar masses, 162.3 grams per mole. Now I can go to work in converting grams into moles using our typical dimensional analysis method. 4.52 grams I'm going to multiply by my conversion factor. Grams has to be on the bottom, so it cancels top to bottom, and we're trying to change it to moles on top. Since I've already got the molar mass, I can plug it in as 162.3 grams per 1 mole of FeCl3. Now all I have to do is divide to find out how many moles that is. So 4.52 divided by 162.3 is 0.0278 moles, which I can finally plug into the top of my molarity fraction. After dividing by 0.5 liters, I get a final answer of 0.056, and since this is the molarity of the solution, it gets units capital M. Here's one final example, slightly different than the previous two. Describing a student creating a 750 milliliter solution that is 2M, or that has a molarity of 2 for sucrose as the solute. Instead here it's asking me how many moles. So unlike the previous two questions, I already know the concentration. It tells me that it's 2M, so I can plug in 2 for the molarity. I already know the volume of the solution is 750 milliliters, which I'll plug in as 0.75 liters. Here, what it's asking for me to solve for is how many moles. So that's essentially the top of this fraction. I like to plug it in as an x, so I can think about this as an algebra problem where all I have to do is solve for x, and that x will represent the moles in the solution. Here, since we're dividing x by 0.75, if I want to get x all by itself on one side of the equation, I'm going to multiply both sides by 0.75. The reason we do that is because it'll cancel out the 0.75 here, leaving me with x equals, then all I have to do is multiply the 2 and the 0.75. This gives me a final answer of 1.5, which remember is the top of my molarity fraction, or how many moles of solute are dissolved in the solution. That concludes this video on molarity. Here's a brief summary.